Why does a calculator, with its rigid precision, always get math right, delivering the correct answer every single time? But why does your phone's voice assistant, despite all its advancements, sometimes stumble, misinterpreting your requests or providing inaccurate information? It's not a flaw or a sign of imperfection, it's a fundamental difference in approach, the distinction between hard computing and soft computing. Hard computing is the classic, traditional approach, relying on rule-based systems, binary logic, the language of computers, precise mathematical models, and exact, verifiable answers. It's like an architect meticulously following a flawless blueprint where every line and measurement is precise. Every calculation is deterministic, same input, same output, predictable and reliable, leaving no room for surprises or ambiguity. This is the backbone of critical systems where mistakes aren't an option, where accuracy is paramount. Soft computing, on the other hand, takes a different route, drawing inspiration from the complexities of the human brain. It's designed to handle uncertainty, learn and evolve from data, and make educated guesses based on patterns and probabilities. It uses tools like fuzzy logic, which allows for degrees of truth in neural networks, complex systems that mimic the structure of the brain to adapt and reason effectively in messy, complex, and often unpredictable real-world situations. Hard computing excels when the rules are clearly defined, the data is precise, and the answer must be absolute and unwavering. Soft computing shines when the problem is inherently fuzzy, characterized by vagueness and ambiguity, the data is incomplete or noisy, and good enough, an approximate solution, is the ultimate goal. Understanding this fundamental split is key to appreciating the diverse ways in which modern technology tackles different challenges, offering solutions tailored to the specific nature of each problem. Hard computing is all about following the program, no guesswork, no deviation. It's a world of absolutes where instructions are executed with unwavering precision. It runs on classical logic and mathematics where every step is predictable. Each calculation follows a strict set of rules ensuring consistent and reliable outcomes. Imagine a calculator type in 12 times 12, and you'll always get 144. There's no room for approximation or interpretation. The answer is always the same. Or think of your bank's transaction system. Every cent is accounted for with zero tolerance for error. The system meticulously tracks every transaction, ensuring financial integrity. This precision is why hard computing powers critical infrastructure, from air traffic control to your computer's operating system. These systems rely on the unwavering reliability of hard computing to function correctly. But there's a catch: hard computing needs a complete, accurate model of the problem. It requires all the necessary information up front to make informed decisions. If the data is missing or the situation changes, it can't adapt. It struggles with incomplete or evolving information. It can't recognize a cat in a photo or handle ambiguity. Its world is black and white. It operates solely on binary logic, with no shades of gray. That's its strength and its limitation: perfect execution, but only when the rules are crystal clear. It excels in structured environments with well-defined parameters. For anything outside those rules, hard computing falls short. It lacks the flexibility to handle uncertainty and complexity. That's where soft computing steps in. It offers a different approach, designed to tackle problems that hard computing can't solve. Soft computing thrives on ambiguity and complexity, stepping in where traditional computing struggles. It's designed to handle the uncertainties and nuances of real-world data, offering solutions that are robust and adaptable. It's modeled after how humans think, using patterns, intuition, and approximation, rather than relying solely on precise formulas and rigid logic. Artificial neural networks, for example, are a cornerstone of this approach. They learn by example, identifying patterns and relationships without being explicitly programmed with specific rules. Show a neural network thousands of cat photos, and it learns to spot cats, even new ones it has never seen before, showcasing its ability to generalize and adapt. Fuzzy logic, another key component, allows for shades of gray, not just black and white, enabling systems to handle imprecise or incomplete information. A washing machine with fuzzy logic senses somewhat dirty clothes and adjusts the cycle accordingly, optimizing water usage and cleaning time based on the specific load. Voice assistants like Siri or Alexa use soft computing to interpret your speech, even with background noise or accents, understanding the intent behind your words. They make educated guesses, not perfect decisions, but they work effectively in the real world, providing useful assistance and information. Soft computing is about flexibility. adapting to messy, unpredictable data, and extracting meaningful insights from it. It's not always exact, but it's often good enough to be useful, providing practical solutions where precision isn't paramount. That's why it powers so much of today's AI, enabling systems to learn, adapt, and solve complex problems in a human-like way. Hard and soft computing aren't rivals, they're complementary. Hard computing is precise and reliable, perfect for math-heavy, rule-based problems like banking or scientific calculations. But it's rigid. If the data is messy or the rules are unclear, it can't cope. Soft computing is flexible and adaptive, great for pattern recognition, language translation, and recommendations. It learns and improves, but its answers are approximations, not guarantees. The key is matching the tool to the task. Need exact mortgage calculations? Use hard computing. Want to recommend movies or recognize faces? Soft computing is your friend. Understanding which approach fits your problem is crucial for building effective systems. The smartest solutions often blend both. The future belongs to systems that combine hard and soft computing. Take self-driving cars. Hard computing runs the brakes and engine with perfect precision, while soft computing interprets the world outside. In medicine, soft computing analyzes scans, while hard computing manages records and equipment. This hybrid approach is everywhere. Robust, reliable frameworks powered by adaptive, intelligent layers. Hard computing built our digital world. Soft computing is making it smarter. Together, they let technology see, hear, and understand. The real power comes from knowing how to weave them together. By blending precision with intuition, we're building a more capable, responsive world. That's the future of computing.